All right, welcome to the Solving Exponential and Logarithmic Equations lesson. So what we're going to start with is solving some exponential equations. Now, we have solved exponential equations before. We've solved exponential equations like 2 to the x equals 8 and way more complicated ones, right? But we knew what that was, or even 2 to the x plus 4 equals 8. But we can rewrite those as the same base. We've also seen ones, I went to erase that, we've also seen like 4 to the x equals 7 and had to estimate the answer and then use our calculator to get a decimal approximation. But now we're at the point of where we actually know how to solve any exponential equation. Why do we know how to do that? That's because we know that exponential functions and logarithmic functions are inverses of each other. So I can use exponential functions to solve logarithmic functions and logarithmic functions to solve exponential functions. And that's what we are going to do in this lesson. So this says solve for x. So it's e to what power gives me 7. Remember, e is just a number. It's a number in between 2 and 3, about 2.7 approximately. But we don't know we don't know what power we bring it to get 7. So, and we can't rewrite them as the same base. So what we're going to do here is we're going to use logarithms to solve this. Now, I know 2 different ways to do this. Like, I know more than 2 ways, but 2 ways that I can think of, like off the top of my head, that are very similar yet different to do it. So I'm going to show you both ways, but then I'm going to lean towards one because you'll see that it's less work. Okay? All right, so one way to do this is to say that since it's in exponential form, you're going to rewrite it in logarithmic form. So remember, to rewrite it in logarithmic form, the base of the exponential function has to be isolated with just the base and the exponent, which this one is. So in other words, like if there was a 3 in front of this, I'd have to divide both sides by 3. If there was a plus 6 over here, I'd have to subtract 6 from both sides. But my base and my exponent are isolated. So what I'm going to do is I'm going to rewrite it in exponential form. So I'm going to write down log, my base is e, of 7 equals x. Now, log base e is just natural log, so we have natural log of 7 is equal to x. And there is my exact answer, okay? But it doesn't ask me for my exact answer. It asks me, if necessary, round to the nearest thousandth, which this case, we're going to end up rounding. But if it asks me for exact, that would be my exact answer. So let's go ahead and do that. Ugh, love when this happens. Just fighting for a smaller space for the calculator. Okay, so we're going to do natural log of 7. And we get 1 point approximately. X is approximately 1.946. Okay, now if I would have done log base e of 7, I don't have a log base e, so I would have to do log 7 divided by log e in my calculator. And if I did log 7 divided by log e, notice you get the exact same answer, okay? So another way of doing this is that you can use logs to solve both sides by logging both sides, right? Once you do to one side, you can do to the other. Since this has a base of e, you could natural log both sides instead, or log, it doesn't matter to me, but if you wanted to, you could natural log both sides. So natural log of e to the x is equal to natural log of 7. And then we can use our property that says exponents you can bring in front of logarithms. So you have x, natural log of e is 1, so times natural log of e, which is just 1, is equal to natural log of 7, so x is equal to natural log of 7, okay? Either way is fine. The first way is actually more effective in the long run. It's like less steps. It seemed like this was easier, but when there's more steps, the first way is more effective. So that's the way I'm going to try to do, but I might switch it up at some points. All right, so this right here, my exponential function is not isolated, so the first thing I'm going to do is divide by 3, and we get 2 to the x power equals 14. So I cannot rewrite 2 and 14 to have the same base because I can't write 14 as a base of 2. So I am going to rewrite in exponential form. So once again, you could log both sides, bring the exponent in front and divide, or you can log both sides, or you can rewrite in exponential form. So I'm going to do log base 2 of 14 is equal to x. So once again, this is my exact answer, right? If it asks for my exact answer, it's log base 2 of 14, okay? But I also want to get a decimal approximation, so now I have to put that in my calculator. So what I'm going to put in my calculator is log 14 divided by log 2, right? And I actually like don't have to log 2, sorry. I don't always have to do it this way. Some of you have calculators that are, if you could actually type log base 2 of 14, but not everyone has that, so I don't want to even go that route. So for this, 3 decimal places, 3.807. Okay. One last one here, I thought, yes. So the base is not isolated, so I'm going to divide by 4. We have e to the 2x is equal to 5/4. And then I'm going to rewrite in logarithmic form. So since it is a base of e, I can use natural log instead of log base e. So I'll do natural log of 5/4 is equal to 2x. And then divide both sides by 2 or multiply by 1/2. So once again, that's my exact answer, but we're looking for decimal approximations here. So natural log of 5 divided by 4, or 1.25. And then I like to hit enter, divided by 2, enter, just so I don't mess this up. And I get 0.112. Okay. All right. Next, we have some examples that are a little bit more complicated, so let's go ahead and look at those, okay? This one right here, my base is not isolated, so I'm going to add 4 and then divide by 2. So adding 4 to both sides, we have 2 times 3 to the 2t minus 5 is equal to 15. Divide by 2, we have 3 to the 2t minus 5 is equal to 15/2. All right, and now we can either log both sides or we can rewrite in logarithmic form, which is what I'm going to do. So we have log base 3 of 15/2 or 7.5 is equal to 2t minus 5. So now I need to add 5 to both sides. Log, oops, I put t already here. Log base 3 of 7.5 or 15/2, I do not care. I'm going to put 15/2, and I'm going to put it in parentheses so that I know that it's the log of that, and then add 5, and then I'm going to divide by 2. Right? All right, so log base, oops, clear. So to put this in my calculator, I'm going to do common log of 15 over 2. So common log of 7.5 or 15 divided by 2 divided by common log of 3. That's the change of base formula, remember. Close the parentheses. Notice I close the parentheses in the 7.5. Enter. I'm doing orders of operations for it so I don't mess it up. Plus 5, enter. Divided by 2, enter. And I get approximately 3.417. Notice I'm terrible at making tildes. We've already discussed that before in other videos. 3.417. Okay. All right, let's move on to the next one right here. So in the next one right here, we have a trinomial equal to 0, and it's a quadratic trinomial because I see a square in there. Well, not in the form that it is. I can make it a quadratic trinomial. So there's multiple ways of doing this. One way is using u substitution. So if you would like to use u substitution, you can. But another way of doing it is looking at as e to the x is looking at it as a moment for like its own variable, like itself. So what I'm going to do is I'm going to use u substitution. If you choose not to, that's fine. So what's confusing about this? The e to the x. So what I'm going to do is I'm going to say let e to the x, let u equal e to the x. And every time I see an e to the x power, I'm going to use u instead. And this is called u substitution. So this is u squared minus 3u plus 2 equals 0. And now I'm going to factor this and solve for u. So two numbers that multiply to give me 2 and add to give me negative 3. So that's u minus 2 times u minus 1. So those multiply to give me positive 2 and add to give me negative 3. So I get u equals 2 and u equals 1. Now, here's the thing. U was never in the problem. I put u in the problem because I was, my brain was hurting. So now I'm going to replace u with e to the x. So we have e to the x equals 2 and e to the x equals 1. So e to the x equals 1, I do not need a calculator for, okay? I know in order to e to what power gives me 1, that's 0, okay? So that is 0. Now for this one, I'm going to end up needing a calculator for it because e to what power gives me 2, I don't know. So what I'm going to end up doing is rewriting in logarithmic form. So since there's a base of e, I'm just going to use natural log instead of common log. So instead of doing log base e of 2, I'm going to write natural log of 2 is equal to x. And then I'm going to put natural log of 2 in my calculator. And I get the decimal approximation for that one is 0.693. So my two solutions are 0.693 and 0. Just going to live with that right there. Okay? So that's how I like to do it. If you just wanted to factor this e to the x minus 2 times e to the x minus 1 equals 0, that's great for you. It's not great for me. Okay, moving on to the next one right here. So there are a few ways of working with this problem right here. So what I notice is that I have a 2 to the x on this side and a 9 to the x on this side, and I would like for both of those to be on the same side. It does not matter which side, right? But I'd like for both of those to be on the same side. So I am going to get them on the same side. So what I'm going to do is I'm going to get everything with an x in it on the left side, everything without an x on the right side. So I'm going to divide both sides by 3. So now this is off this side, but that means I'm also going to divide both sides by 9 to the x. So now I have 2 to the x over 9 to the x is equal to 4/3. Yes? Okay. Now that 2 to the x over to the 9 to the x, I can rewrite as 2/9 to the x equals 4/3. See that? Okay. So now I want to know 2/9 to what power gives me x. Or sorry, 2/9 to what power gives me 4/3. I don't know off the top of my head, right? Like I don't know, sorry. So what I'm going to do is I'm going to rewrite it in logarithmic form so that I can put it in my calculator and see. So I'm going to say log base 2/9 of 4/3 is equal to x. So there's your exact answer. What does the direction say of this? I kind of on the same directions. And then I'm going to put that in my calculator. So remember what I'm putting in my calculator? I'm doing log of 4/3 divided by log of 2/9. So we have log 4 divided by 3 divided by log 2/9. Oops, I put an extra parentheses, 2 divided by 9. Enter, and this is approximately negative 0.191. So x is approximately negative 0.191. So the, not frustrating, but the unsettling thing about this is that like, as you're doing it, you're like, did I do it right? Like, how do we check our answers, right? So remember, you just solve for x, so you could always come back to the original problem and do 3 times 2 to the, and then I want that decimal right there and see what that is. Okay, that's that. And then I can do 9 to the, and I need that decimal again right there. Get out of that, and then times 4. And you should get the exact same answer, right? And if you are, because they're equal to each other. So now I know that I did it right. All right, so you can check your answers even though they're a little unsettling. All right, last one. There are multiple ways of doing this, okay? I'm going to show you two, not last one, but last one in this section. I'm going to show you 2 ways of doing this one. I'm not sure which way you will prefer, but I'm going to show you both. Okay, So one way to do this is, once again, I see exponents of x on both sides. I can take this and split this. This is the easier way. I can split this up. Like, I know this is the same thing as 5 to the x times 5 squared. Because remember, if you have the same base, you can keep your base and add your exponents, which is this is that. So I'm just like working in the opposite of that, right? And then you have over here 3 to the x. So now I can do it just like I did the last one, where I'm like, okay, I have 3 to the x power and 5 to the x power, but they're on separate sides. Let's get them on the same side. And then 5 to the x divided by 5 to the x. And then I can rewrite this as 3/5 to the x is equal to 25. And then now I can do it just like I did the last one, right? I can rewrite it in logarithmic form. And then put common log of 3/5 divided by common log of 25 in my calculator, right? And I can get my decimal approximation. So common log of 3/5, which is 0.6, divided by common log of 25, and we get negative 0.5, negative 0.158. Did I do something wrong? 3/5 divided by 3, 25, log base 3/5. Oh, I wrote my log wrong. Oopsies. Take it back, Terry. Okay, I wrote my logarithmic form wrong. I don't know why I realized that, but it's fine. Log base 3/5 of 25 is equal to x, because it's an ugly answer. I don't... Log base, I had it flip-flopped. I'm lucky that I realized that I wrote it wrong. X equals this in my calculator. All right, let's try that again. Log of 25 divided by log of 0.6, or 3/5, negative 6.031. Did I do that wrong? No, I could always check. But I'm going to check in a second when I do it another way. Negative 6.301. Okay, so that's one way, which I think is easier, but like not everyone sees that way right away. Like if you look at the steps, it's not that bad, okay? But another way is saying I need to solve for my exponents. I can't rewrite 3 and 5 to have the same base. I'm going to log both sides. So I'm going to log the left-hand side. I'm going to log the right-hand side. All right, so now why would I do this? Because now my exponents get to come down and they're no longer exponents, because the problem is that I have variables in my exponents. So now I have x times log 3 is equal to x plus 2 times common log of 5. So now the issue is that you have x's on both sides of your equations. So I need to solve for x, meaning I need to get all my x's on one side. So I have to distribute the right-hand side. So this is x times log 5 plus 2 log 5. And the right-hand side is still that x log 3. I need to get all my x's on one side, so I'm going to subtract x log 5 from both sides. So I have x log 3 minus x log 5 is equal to 2 log 5. Then I can factor my x out of these two terms. So I have x times log, you can already see that this is like way more complicated, right? Times log 5, or sorry, minus log 5 equals, and then this is the same thing as log 5 squared, which is log 25. So you can say, ooh, that log 25 is showing up, right? And then I can say that this is the same thing. I can condense these two logs right here and make it one log. This is common log of, when you have two logs that are being subtracted, then you can divide them. Oh my goodness. And then divide both sides by the log of 3/5. Full circle here, all right? And you get x equals that, which, voila. But if you look at the work comparatively, if you can see it as number 7, you should do it. Okay, so now we have some, I was just making to see how much longer this video is going to be because it's already gone quite some time. So now we're going to do some examples of solving logarithmic functions, which is similar but very different, right? So this is solve for x round to the nearest thousandth if necessary. Remember to check the domain. The reason you have to check the domain on logarithmic functions and not exponential functions is because the domain is restricted on logarithmic functions. Logarithmic functions, if you remember, look like this. Right? That's the parent function, which does not go from negative infinity to positive infinity. Logarithmic functions, growth, for example, looks like this. Decay is obviously going like this, right? Well, that's a terrible picture of it. But they have all real numbers, so we don't have to check our solutions and think that they might not work for exponential functions. But for logarithmic functions, we do. We know that the argument can't be negative. So for example, if I solved this and got x is 0, and I plugged it in right here, I would get an argument of -1, it would not work, okay? All right, but let's go ahead and solve these. So, similarly to exponential functions that we had to solve before we used logs, for logarithmic functions, we're going to use exponential functions. So, when it's a logarithmic function and you're like, what to do? Rewrite it in exponential form, okay? So you need your base, which is e. Your power, 2, equals x. So we have x equals, and you put it in your calculator. E to the second power is 7.389. Approximately. I'm not gonna write the approximately, I'm so sick of it. Okay? All right, check your 7.389. If you plug it in here, you don't get a negative argument, you're good. Okay, this one right here. This log is equal to this log, right? So if I went like this and went like this, right? What we do know is that whatever's inside those things that I scratched off, they have to be equivalent to each other for it to be true, right? So we are going to set the arguments equal to each other. 5x minus 1 is equal to x plus 7. Subtract x from both sides, you get 4x. Add 1 to both sides, you get 8. Divide by 4, you get x equals 2. Let's check before I box this to make sure that it doesn't give us a negative argument. If you plug in 2 here, you get 9. If you plug in 2 here, you get 9. So we are good to go. What I don't like seeing is when people go like this. That's an ew to me. It's like, they didn't like jump off the paper. Okay, next right here it's very similar to number 1, but natural log of x isn't isolated. So let's go ahead and get that isolated. Subtract 5 from both sides. 2, natural log of x is equal to -1. We have a choice of what we can do with this too. We can either divide both sides by 2 or bring it as an exponent. It doesn't matter. I'm gonna divide both sides by 2 because I can, right? So I have natural log of x. If it was something other than a number, like if this was a 2, I don't even know, plus, I don't even know. But if it wasn't just a number, if it was another log, for example. So divide both sides by 2, you get -1/2. And then I already know I could stop right here, right? I'm going to stop right here. No, I don't need to stop right here. I was going to say I can't have that answer, but I can. E to what power? E to the -1/2 power gives me x. It can have negative exponents. That's my exponent. All right, so e to the, where are you? There you are. -0.5 equals, x is approximately 0.607. All right, here's the next one. It's just like the last one. It's got 1 log in it. I need my log to be isolated, so I need this to be by itself. So I am going to divide both sides by 2. So I have log base 5 of 3x is equal to, divide both, I forgot to check my answer. And that would be positive, good. If it was negative, I'd be like, not possible. Or that's not a solution. Divide both sides by 2, I get -2. And then I'm going to rewrite an exponential form. So I have 5 to the -2nd power is equal to 3x. 5 to the -2nd power is 1/25 is equal to 3x. Divide by 3, or multiply by a third, and I have x equals 1/75. Right? Yeah. Okay. All right, next one right here. So this is different from the other ones because this has 3 logs in it, right? But 3 logs shouldn't be a big deal because 2 of them are one side. So these 2 right here, I really wish it was 1 log on this side because then I can just set the 2 logs equal to each other. And I know how to make 2 logs 1 log. If it's addition, I can condense them by saying that I'm going to multiply the 2 arguments. So I'm going to do x minus 2. I'm going to put this in brackets here so I don't get lost. Times 2x minus 3. And that's equal to, and then I'm going to write this as an exponent because I don't want to divide both sides by 2 because that is scary on the left-hand side, right? So I'm going to write natural log of x squared. All right, so now I can set my arguments equal to each other. So multiplying this out, I'm going to multiply this out right here and set it equal to this. So we have 2x squared. Outer is negative 3x and inner is negative 4x, so minus 7x. Last is plus 6 is equal to x squared. Subtract x squared from both sides, and we have x squared minus 7x plus 6 equals 0. Factor, we have x minus 6 times x minus 1 is equal to 0. So we get 2 solutions, x equals 6 and x equals 1. Now remember, we have to check our answers. Did I check it on the last one? 1/75. That's still going to give me a positive argument. Got to get better at it. All right, checking 6. 6 minus 2 is 4. Check. Plugging in a 6 here, that's 12 minus 3, which is positive. Positive, so that's good. Plugging in 1. 1 minus 2 is negative. Out. There we go. We finally got one that didn't work. All right. Oh, I was going to say last one on there, but yep, here we go. So last one is a word problem. It says you have deposited $500 into an account that pays 6.75% interest compounded continuously. How long will it take for your money to double? Okay. All right. So we know that we're using the PERT formula since it's doubling, right? Which was A equals A naught or P times E to the RT. Okay. All right. Do we know our initial amount? Yeah, it's 500. Okay, we put in account, and we have E to the, it pays 6.5% interest, so that's 0.0675. How long will it take? We're looking for T to double, so doubling is 1,000. So really, we didn't even need to know that we had 500. We could have put A naught and 2A naught, right? Like, we just know we would have had it, when we divide both sides by 500, we're going to get 2 over there no matter what for doubling. So we didn't even need to know the initial amount if we were looking at double. So we have 2 equals E to the 0.0675 T. Okay, so this could have easily been the first problem that we did. We want to solve for the exponent, okay? And I don't know E to what power gives me 2. So we're going to use logarithms. Since the base is E, I'm going to use natural log. So I have common log of E. So instead of doing common log of E, argument 2 equals, I'm not going to do it that way, right? I'm just going to do natural log of 2 is equal to 0.0675 times T. And then to get T by itself, I'm going to divide by 0.0675. Put that in my calculator, and it's going to give me an approximation. Hey, calculator, natural log of 2, don't forget to close the parentheses on your 2, divided by 0.0675, enter, and I get approximately 10.269 years. That's how long it'll take to double. All right, that's it for our very long screencast, but hopefully you got an explanation of both of those solving problems.